Hello everyone and welcome back. Today we're diving into episode 65 of our series. Let's talk about a classic yet tricky problem in distributed systems. What happens when you accidentally process the same message twice? Imagine your system sending out two identical packages, or worse, charging a customer's credit card twice for the same purchase. Suddenly, what seemed like a minor glitch becomes a major headache. This is where the concept of idempotency isn't just a nice to have. It's a hard requirement, especially when you're working with message queues. So, what exactly is idempotency? In simple terms, it means that performing an operation multiple times has the same effect as performing it just once. Think of pressing an elevator button. You can press it once or 10 times, but the elevator is still only called once. That's an idempotent action. In the world of software, this principle is crucial for building reliable systems. We'll explore how to achieve this through careful inspection of our processes and implementing smart deduplication mechanisms. These aren't just fancy buzzwords. They are the tools that will save you from those nightmare scenarios of duplicate processing. Let's use a real-world metaphor to make this clearer. A logistics company. Imagine you're running a warehouse. Your delivery guarantee is at least once delivery. This sounds good, right? The customer will definitely get their package. But it also means there is a chance they might get the same package twice due to some hiccup in your system. Like a network timeout that makes you think the first delivery attempt failed. Now, if this package contains a simple welcome letter, a duplicate is no big deal. But if it's an expensive product, sending it twice is a costly mistake. To prevent this, you need a system to track what you've sent. Every package, or in our case, every message, needs a unique identifier. Think of this as a unique order number or a tracking ID. When a package arrives at the processing center, the first thing you do is check your records. Have we already processed this specific order number? If the answer is yes, you simply discard the duplicate package. This is deduplication in a nutshell. You're checking for uniqueness before taking action. But what if your system isn't just about sending packages? What if it's about financial transactions? Let's say you're managing a ledger. If a deposit $100 message comes in twice, you can't just blindly add $100 to the account each time. That would be a disaster. This is where business idempotency comes into play. You need to design your business logic to handle these repeats gracefully. For example, your ledger system could check the unique transaction ID. If it has already seen that ID, it knows the transaction has been processed and can safely ignore the duplicate message. The key is to build this check directly into the core logic of your application, ensuring that even if the message queue delivers a message 10 times, the actual business operation, like crediting an account, only happens once. This brings us to a core insight about modern system design. In most distributed messaging systems like Kafka or RabbitMQ, the default and most common delivery guarantee is at least once. Exactly once. Delivery is notoriously difficult and often computationally expensive to achieve. So instead of fighting the nature of the messaging system, we embrace it. We accept that duplicates might happen and shift our focus to making our application's business logic robust enough to handle them. We design our services to be idempotent. This means the responsibility moves from the infrastructure to the application layer. Your code must be smart enough to recognize and discard duplicates, ensuring that repeated messages don't cause unintended side effects. This mindset shift is fundamental to building resilient and predictable distributed systems. So how do you actually implement this? There are several patterns. A common one is using a combination of a unique message ID and a persistent store like a database. When a message comes in, your service first checks if the message ID already exists in your processed messages table. If it does, you know you've seen it before and you can just acknowledge the message without processing it again. If it doesn't exist, you start a database transaction. Inside that transaction, you perform your business logic like updating the user's account, and then you insert the message ID into your processed messages table. Because this all happens within a single transaction, it's an atomic operation. Either both the business logic and the ID logging succeed, or they both fail and roll back, preventing any partial state. This database-driven approach is very reliable. But what if performance is a major concern? Hitting the database for every single message can add latency. This is where a faster in-memory store like Redis can come in handy. You can use Redis to keep a set of recently processed message IDs. Checking for an ID in Redis is incredibly fast. When a message arrives, you first check if its ID is in the ready set. If it is, you drop the duplicate. If not, you add the ID to the set with a time to live or TTL. The TTL is important. It ensures that your ready's cache doesn't grow indefinitely with old message IDs. You might set it to a day or a week, depending on how long you expect duplicates to potentially arrive. This hybrid approach gives you both speed for the common case and the safety of a persistent store for long-term consistency. Now let's tie this all together. By implementing these deduplication mechanisms, you're making your consumer idempotent. You're building a system that can gracefully tolerate the imperfections of at least once message delivery. Whether you use a database, a cache like Redis, or a combination of both, the principle is the same. Check before you act. This simple rule is the foundation for preventing all sorts of costly and embarrassing errors, from double billing customers to sending duplicate notifications. It's a powerful technique that separates robust, production-ready systems from fragile ones that fall apart under real-world conditions. Building idempotent consumers is a non-negotiable skill for any developer working with message queues. But hold on, we're not quite out of the woods yet. Let's say you've perfectly implemented idempotency in your message consumer. Your database is always correct, no matter how many duplicate messages you get. You're feeling confident. But then users start reporting strange behavior. They see stale or incorrect data on your website. What's going on? Your core business logic is solid, but there's another layer that can cause trouble: the cache. Your caching layer, which is supposed to speed things up, can sometimes remember things for too long. It might hold on to old data, creating a disconnect between what is true in your database and what is being shown to the user. So even if your message consumption is correct, your cache can still introduce its own set of problems, making it seem like your idempotency logic failed. In our next discussion, we're going to unravel this very problem. We'll explore how caching interacts with message-driven architectures and why a naive caching strategy can undermine all your hard work on idempotency. We'll look at cache invalidation strategies and how to ensure that when your data changes, your cache reflects that change promptly and correctly. It's a fascinating challenge that sits at the intersection of data consistency, performance, and user experience. Make sure you join us for that one. Thanks for watching today, and if you found this helpful, be sure to like, subscribe, and hit that bell icon so you don't miss our next deep dive. See you then.